All right, guys. So for today's session, we are going to take a look at another data set. And in this data set, we are going to look at some handwritten digits. And then we're going to try to see if we can convert those handwritten digits into the actual number. So something like this. So we have data for each image. So let's say there's somebody has written a number 9 like this, then we want to be able to convert that to the number 9. And if somebody has written the number 8, then we want to convert that to or realize that's actually the number 8. And there might be different ways people have written 8, and we still want to get the number 8, right? And then so we have data that gives us the label. We have the handwritten image data also, and we want to. So this falls under what is called object recognition, and sometimes it's called OCR. But in this example, this is what the data actually looks like. So imagine that we've so this image is broken out into a bunch of pixels, right? So this is a small image with 28 pixels by 28 pixels, okay? And the pixels in which we find that the drawing actually occupies these pixels, those have a high value, right? A high value. And the pixels where there is nothing is written in it have a low value, right? And these all are numbers. These could be values between 0 and 256 or something like that, depending on the resolution. Okay, but for each image like this is a 28 by 28, right? But in the data set, this is converted into one row. Okay, so it's converted into one row that goes from so 28 by 28 is what, get a calculator out here. 28 by 28 is 784. So 1 to 784 columns, or maybe 0 to 783 actually. And we're just kind of transforming this 28 by 28 into a 1 by 784. So you have the first 28 rows and then the next 28 rows, right? Like that all the way to 784. And then each of these values are the data points. And then we also have another column, which is the label, right? So for this one, that label would say 9, right? And then we'll have another row for the next number, right? Suppose we had the number 8, then we'd have the corresponding row, and then this label would say 8. Okay, so this is what the data looks like, and this is a very commonly used data set called MNIST. It's available out there, but it really helps us to understand certain concepts. All right, so essentially what we're doing is we're going to try to take these images here and the image data and try to predict these numbers. All right, that's what we're trying to do. So let's take a look at the actual data and then start building models given what we already know. So previously we have already studied among classification models here, we have already looked at naive Bayes, logistic regression, and support vector machines. And we've already done that in the past. But this time, so let's start with an SVM and see where it goes. Okay. So let's get started. So start with initializing our libraries. So pandas and will also for pre-processing, right? We or model selection, we want train test split. And we from metrics, we were going to get in the classification report because that is something we're going to use to see how well the models are doing. If you remember, we did the ROC AUC score, we did classification report when we were doing all the classification models. So we'll just use classification report for now. All right, and let's go ahead and then load the data. So this data load is a slightly larger file, and that file should be available to you online. I would have also put a link to the data. So let's see here, pd.read CSV. It's converted into CSV, by the way. Sometimes you get this data in binary form, but put it in CSV form for ease of use here. Right? So it's under a folder called handwriting, and there's actually two data files here. If you go and see, there's two data files. One of them is, so one of these data files is called handwriting digits, and the other is handwriting digit score. So the difference is that in handwriting digits, we actually have the labels. Okay, we have the labels. That means we know what the actual labels are. So we can use that for training and testing and stuff like that. However, in this handwriting digit score, it's missing one column, which is it doesn't have the label. So that that's like a set of data that we're going to see. Can we predict what those are? And then maybe we can look at it visually and see how well we did. All right. So we're going to use this handwriting digits file first to do the training and testing. CSV, okay, and then let's look at the head. Go back to our notebooks. We're right here. So as you can see, we have pixels from 0 to 783, and then which is the 784 columns, and then the label column, right? Let's just quickly describe run a quick describe of the columns to see what the range of values are. So if you see that's these pixels, the range of values is from 0 to 254. So it's it's the typical pixel intensity type of data. So each value in here, because it's a big table, you can't see it, but it ranges from values between 0 to 254. Okay, and of course the label column, there's 10 digits, right, from 0 to 9. Okay, so suppose we were to break this image up like this. Suppose we broke this image up into like something that looks at this part of the image. No, everything has to be thicker. Okay, suppose I look at this part of the image, bottom half, let's call it bottom half. And we have another one for top half. Okay, then I'll know that I'll be able to catch 8, I'll be able to catch, but for a 6, it's got the bottom half. But maybe I want to look for something like this as well, right?
Maybe I want to look at these 3 pixels at a time. I want to look at these 9, yeah, but then I also want to look at those, see if these 3 pixels are filled in. That will give me an idea that it's actually a 6, right? So we're breaking up the image into parts. So if now here's the idea now. If we're able to take, so I'm going to take this image, okay, I'm going to convert it into one vector. So this would be 0, 1, 0, right? 0, 1, 0. Okay, the top. That's 0, 1, 0, 1, 0, 1. I'm going to keep going that way. Okay. I'm writing out this 1, 0, 1, 1, 0, 1, 0, 1, 0, and then the same thing, right? 101, 101, 0, 1, 0. Okay. Everybody with me so far? I just took this image and I converted it into a bunch of zeros and ones. And if I took this image down here, and I also made the same vector, okay, so this would be, what would it be for the first 3? There's nothing in there, right? 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, right? All right. But somehow we have to go from this, again, now we're trying to automate this, right? We want to try to program the system to take this and spit out a 6. We want to program the model to take this and spit out an 8. So what were we doing in our brains? We were breaking it up, right? So let's break it up into let's say into 3 values. Top, circle. Do you have a top circle or not? Bottom, circle, and diagonal line. Okay, this is the 3, 1, 1, 2, and 3. What we're looking for. And we do the same thing for this image. So if we're able to take this and transform this into, and then get a value of, yes, does this have a top circle? Yeah, I want a value of, let's see, draw. I want a value of 1 for top circle, because there is 1. I want a value for bottom circle, yeah, or some high value. And then for diagonal line, I want it to say 0. And then the bottom should be no top circle, there should be a bottom circle, and there should be a diagonal line. If I had a way to go from this to this, then after that I could take this and then say, oh, anytime you have a top circle and a bottom circle and no diagonal line, whenever that happens, then I'd be able to say, let's say this is 8 or a 6. Okay, that's all I'm trying to predict. I have 2 types of images, 8s and 6s in this. And so I want my value for 8 to be a 1 and my value for 6 to be a 0. And then down here, eight and 6. And I want these values to be flipped. I want to say 0 for 8 and 1 for 6, right? So this is my way of getting from the image down to, oh, this is an 8, it's not a 6, and this is a 6, and it's not an 8, right? But I made assumptions that I could go from here to here. Somehow. How do you go from one vector to another vector? What have you learned so far that helps you go from one vector to another vector? What classes have you taken that transforms one vector to another vector? In linear algebra, if you multiply this by something, you can try to get it. So if I have a 1 by, how many is that? So this is a 1 by, what is it? Is it 18? 21, right? Yeah. This is also 1 by 21. So if I have a 1 by 21 and I need to get a 3 by 1, what do I need to multiply that by? Remember back to your linear algebra days. So if I have a 1 by 21 and I need to multiply it by what to get a 3 by 1? Come on, you guys remember this? Anything you multiply, the column number should match the row number, right? Whenever you do a matrix multiplication, the column number should match. So this has to be a 21 by 3. So if I have this matrix, then I can multiply this times that to give me this. I'm okay. But I can't have a different one for each because all of them have to be pushed through the same transformation. That's the trick. So how do I come up with one of these that if I multiply this times that, it properly activates these parts of the vector and deactivates this one? And when I multiply this vector by the same one, it deactivates the first one and activates the second. If I could come up with that vector, I'm good, right? Then all I would need to do, a new image comes, I get the values of 0 and 1, multiply by that vector, get this, and then I transform that again into something else, right? What's my second transformation? This is my first transformation, right? Let's call this layer 1 transformation. And then over here, what do I need to multiply for a 3 by 1 to get a 2 by 1? Three by 1, 1 and 2 by 1. What is it? 3 by 2 or so if I do this, match on the outside, it'd be 1 by 3. And then that comes to 3 by 2. We can do 2 by 2. I transform it, right? Transpose it, sorry. So what should this be? And I'm going to transform this, right? So I'm going to take 3 by 1 transpose, which gives me a 1 by 3, and then by a 3 by 2. to give me a 1 by 2, and then I transpose that back to get this, right? Okay. Either way, I need a 3 by 2. This is what I need to figure out, right? I need to get this. So I have this one matrix to figure out, and I have this one matrix to figure out. But if I figured those out, then all I need to do is any new vector that comes. So this method that we just walked through, this method of going from the image to the image here, the image to a layer 1 transformation to a layer 2 transformation, and then finally get to your output. Because this is how our brains work, there's a nice name for this method, and they have names for all the different steps that we just went through. The fact that we broke this up into pieces, and it wasn't by coincidence that we decided to go with zeros and ones. In our brains, when we process an image, there are parts of our brain, neurons in our brain that get lit up whenever certain things are activated and are turned off whenever other parts are deactivated. So because of that, there's names for all of these things. Again, this is just terminology, okay? These are known as, let me just draw that actually. These are known as neurons because we're activating and deactivating them. And this is a network of neurons, right? Because this is connected to this, and this is connected to this, and then that's connected to that, and all together they give you the output. So it's a network of neurons. And so what is this method? What do you think this method is called? And so it is called a neural network. Okay, but there's one big gap. How are you going to figure what these are? Who's taken OR models? Yeah. Anyone else? Yeah. All right. When did you guys take it? Last semester. Okay. This is your decision variable. Okay, these are the values that you're going to change. You're going to keep changing these, but you need an objective, right? You need something to say whether that's a good combination or a bad combination. What's a good objective? Well, if I look at this 8 and 6, if this is the prediction, if I say that, hey, hold on, I already know this is my truth. I already know that this should be a 1 and this should be a 0. Right? And I already know that this should be a 0 and this should be a 1. So if I take the differences between these values, right? This is the prediction. If I take the truth minus the prediction, yeah, and then I try to minimize this. If I try to minimize the difference between the truth and my prediction, and I solve for the values in these matrices. Right. Solve for the values here, and the values here. Then it will help me get all my parameter values, and it would minimize my error. That means I'm predicting the numbers right, and I'm predicting the other numbers right. I'm getting 8s when I want and 6s when I want. So let's actually do that. Why don't we do that in Excel? Right. So I prepared this example. Let's see how well that works. So here's a representation of my 8 and my 6 here, right here. Yeah, my 8 here, my 6 here, and I've converted that to my vectors here. And this is my 3 by 21 that I'm trying to guess, right? I'm trying to guess this. And I'll tell you a little bit about what this is. And then these are my circle on the top, circle on the bottom, right? Angular line. And then here's my another 3 by 2, but I put it as a 2 by 3 because it's transposed. And then I want to get this, and I want to figure out whether my 8s is my 6s. So here, let me start with a different starting point. So I want these numbers, I want to play around with these numbers. But before we, all right, no, so I want to play around with these numbers. Let's see, let me take the other matrix. So you can give some starting values to these matrices, but and here's my error. I'm taking the difference between the values that I have for 8 and 6 with the actual truth. Taking the differences here. And now, did you guys use solver in class? Yeah. Okay. So if you set this up properly, then you will see that I'm trying to minimize AT3 by changing all the values in these tables. I put some constraints around them, right? And let's see if it works here. Okay, it's converged to a solution. And look at this. It's got the predicted one for 8 to be a 1, 6 is 0, 0 and 1, which is exactly what we wanted. So our error is 0. And it has tweaked and modified the values of this table. So now any new image that comes, if we just multiply by this, get the values in the intermediate level, and then multiply that again, you'd be able to decide whether it's an 8 or a 6. Okay. Now, what neural networks really do behind the scenes is they're really good at calculating these very fast. Okay. What's the difference between, why is it so much faster than everything we've done before? Because it uses matrix manipulations, and matrix algorithms come really far. You can do really fast matrix calculations to come up with these numbers. Right? Now, a little bit more terminology before we jump back into our code. So this calculation here, right, is a multiple. So I'm multiplying this by this, right? Just like we said, we're going to transform it. But then, just because we multiplied it, sometimes some part of the image might have been shaded slightly. You don't want it to activate too much. There's a minimum threshold you want it to exceed before you actually count it. And that's what that bias is. So you say, okay, do the multiplication and then just take out anything that's not above that minimum threshold. Okay, so that's what you see here. I do the matrix multiplication and then I subtract whatever's in my bias. Okay, so that's like a minimum. Only if this multiplication value is higher, take it. Otherwise, leave it. So I do my multiplication and I get this, but this is not ones or zeros. That's not a 1 or a 0. That's just some number that's anywhere from minus infinity to positive infinity. How do I take this and make it into ones and zeros? What's the function to convert from negative infinity to positive infinity to a value between 0 and 1? What's that? Well, scaling does it in your data, right? So actually, yeah, that's scaling is, what does scaling do? How does scaling do that? So one way to do that, by the way, guys, is let me just write that down. One way to do that is So if you have data that's all the way from negative infinity to infinity, and you want to get a value, x is between negative infinity and y, you want it between 0 and only used him. So any value down to minus infinity is given a value 0. Positive infinity gives a value of 1. Anything in between is somewhere in between. This is known as, you guys remember this function? This is the sigmoid function. So if you take any value and sigmoid function, y is 1 over 1 plus e to the minus x. That's how, this is the formula of this function. So if you have any value x from minus infinity to positive infinity, if you plug it into this, you'll get a value between 0 and 1. Okay, so we use that function in our Excel. See this? This value is 1 over 1 plus the exponent of negative this. So that converts it to a value of 1 or 0. And is that what we wanted? That's what we wanted, right? We wanted it to activate. So that's this function that we just applied here, the sigmoid function, taking the matrix manipulation. All of that together is known as the activation function. So coming up with the parameters of the activation function is what neural networks do. Okay? And it does it really fast. Okay? All right. This explanation, guys, by the way, of neural networks, I have not seen it out there because it requires you to take a real example and walk through it. So I would suggest you really think about this. If you understand this part, then you will know everything behind what neural networks do. Most folks that try to teach neural networks, they'll go straight into the libraries, and you will sort of understand that, yeah, it uses neurons and yeah, it kind of goes through, but you don't know why. Right? So this tells you why neural networks, why do you need neural networks? Is faster. Why is it faster? Because it's doing matrix manipulation. But why matrix manipulation? Because we use matrices to come up with these functions, and then we layer them one on top of the other to get to your output. Okay. All right. So, okay. So the SVC got done. Took 5.5 minutes.
All right. So now let us go and build the neural network for this. Okay. Let's see. Build neural network model. And okay, start that. So we can, so let's see if we can get some syntax for that. So we say sklearn neural network. So among the different neural networks, we're doing classification here, right? We're trying to figure, it's a classification problem, not a regression problem. And MLP here stands for multi-layer perceptron. So because we have multiple layers, we would be using the multi-layer perceptron. So that's in .neural network. So .neural network import MLP classifier. But the nice thing is you define it here. There's some parameters you can set and then do the fit and predict so that the syntax is exactly the same, which is kind of nice, right? It's nice that sklearn keeps all of this in, and even as you go to some of the other libraries, a lot of times it would be kept very similar, but you do have to look for some modifications in syntax if you use other libraries. Okay, so let us do neural network and import MLP classifier and go with MLP classifier. Go and call it for neural network, and then just use that term. And then finally, we want to be able to run this. So let's see if we need to do anything else here. All right, let's run the neural network now for the same problem. The main thing is for us to see how long it takes and what the performance would be like, all right? So let's give this a few seconds here. I'm going to go on mute for a few seconds as that comes up. All right, so that looks like it, so it took 30 seconds compared to 6 minutes of the SVM. The overall accuracy seems a little better, right? 0.96 to 0.97. We see the F1 scores, goes, the lowest is a 0.96. Here we did see some 0.94s. So, a model that's better and in a much shorter time, right? 30 seconds versus 6 minutes. So I guess we can see that neural networks are definitely very useful in such problems. And but let's see if we can look at, remember we had another data set, right? We had the handwriting digit score data that we don't really know what that looks like. So let's go ahead and use this model to predict the numbers in that data set. So, but let's first visualize what that data is. Right, so let's say load data for scoring. Data that you don't have labels for is typically called scoring data. It's called like score, and let's say read CSV. It's in our data folder, handwriting, and this was handwriting digits score. So this is a much smaller data set with a few digits. Oh, and remember, we need to scale this. Whatever you do to your training data, you need to do to your scoring data also. And then maybe it would be nice for us to visualize what these digits are before we do the prediction so that we can check. Right, so I'm going to write a little bit of code here. Just bear with me. I'm not going to explain this. This is just for visualization. Remember, we want to do the image show for this, and then we say X score, but then I want to put this in a loop because there are a number of images there. So if we say for I in range call times row, if I do that, and then I set my call and row to be 10 and 4, and and I also need to I want this to be a grid, right? So my figure should be, fig size is, each image should be 12 by 10 just so it fits in my screen. All right, I've got 40 images here, so I'm going to put them in 4 rows of 10 each. And then I want to show X score of I, and remember we had to do the reshape, 20 by 28, and then I need to put each one of these in what is called a subplot. So I'm going to put them in a subplot, say roll call, and then go into the next one. Right. Go to show. So this is rendering now all the handwritten images that have not been, so we don't know that the model has not seen these before. Okay, so these are some handwritten images, digits. This is interesting, right? I wonder whether the model will think of this as a 4 or a 7 or a 9. All right, so let's go ahead and now apply our neural network to these digits and see if it can accurately predict them. So we're going to, so normally we would just say, I'll just put some notes here. So here we are trying to view the new and written digits. And then we are now going to predict the new and written digits, okay? Predict the label for the new handwritten digits. All right, so basically we would have just said model neural network dot predict, and we would have just given a score. But we'd like to see it in a little bit more formatted way. So I'm gonna, again, write a few lines of code for formatting. So again, bear with me here. I'm gonna try to put this in a loop. So let me say, again, for I in range of call times row, put this in there. And I want to do it for now for I, show me the value for I. Put a print statement here so that I can actually see it. Print that and then give a space after each number. So some of this might help you guys also as you do some of this. All right, but then whenever I reach the end of a row, I want to give it next line. So I'm going to figure out if I'm at the end of a row or not. Mod I and call. So we know when the different when the mod of that is equal to 0, that means I know I've reached the end of the line. Just go print new line. Right. Okay. By the way, I'm using NP here, which is the NumPy library. I don't think I added the NumPy library here. It's a good library to add, I guess, in general. Okay. So now as we go here, all right, let's see if, okay, now it's starting to predict these numbers using the input. All right, so let's see, the first row, so we would have said 2090370303, 20993703. So it misrepresented this in the fourth digit here, the 9. It thinks this is a 9, right? So so there's one error there, but let's see the rest of them. 57404339190. So we've got all of that right. 91. So it looks at this as a 1, which I guess that's what we would have probably said too. And then the last row it seems pretty much all right. So pretty decent. It's pretty nice that a simple model, simple neural network like this is able to take a problem like this and solve it, right? Which is and to do it so quickly. So hopefully that's a good lesson to be learned here. Now, we've also heard the term deep neural networks, right? In industry, you hear the term deep neural networks. And basically what that is it's just that you see in our example here, we only had one layer. Well, the more layers you add, you're just adding more hidden layers, then it's called a deep network. Okay, that means it's deeper because you have more layers. So this is already a deep network because it has 2 layers. So so let's go ahead and build a deep neural network here. So remember that, so in NLP classifiers, in neural networks, the default is that it has 1 layer with 100 neurons in it. Okay, that's the default. If you go and look into the, let's see, hidden layer size, you see that the default is, it just says 100 comma, which means one layer with 100 neurons. Right? You see the ith element represents the number of neurons in the ith hidden layer. So if we wanted more, we just put 100 comma whatever amount we need in the next layer, and then comma if you want another layer, and then how many neurons we want in that. So let's just do that very quickly. Just for completeness here, let's say build deep neural network. Okay, and it's still MLP classifier. There's of course other libraries you could use as opposed to sklearn, but if you want to do it in sklearn, you basically go in here. Okay, let's say this is a deep neural network, and here we'll say hidden. So previously we didn't say this because the default was 100 and we just went with the default. But here let's go ahead and just say, in addition to the first 100, this is the default. We'll add another layer with 100 neurons in it. So it has 2 layers, each one with 100 neurons. And let's go ahead and run that. So while that's running, let's go back to our notes here and fill our tree here of how we think about these, right? So we have if the target is continuous, we go down the regression path. Target is discrete, we go down this classification path, and then we've said that when the features are independent of each other, then you can go with naive Bayes, and this is typically a good one for healthcare types of data sets. If they're not independent, we can't say that they are independent, then logistic regression is the most basic model there. But both of these are probabilistic models. But then if you have outliers, and then you basically can use the SVM, which, as you remember, tries to create a separation between the 2 different classes, or all the different classes. But then whenever the what I would say is, whenever your problem is more complex, that means you have a large number of, if you have a large number of columns like we have here, 784, but then a lot of these examples you might have 10,000 or hundreds of thousands, maybe even millions of columns. Think of video data processing, right? Just frames per second and have all that data. Then there's no way that some of these basic models would be able to do anything. And so we go into the artificial neural network. And so regular neural networks are called artificial neural networks. And there are some other sort of special cases here. I'm just going to write them down here for completeness. So when you add layers, for better performance, better accuracy, you end up with deep networks. And I'm not going to talk too much about these, but if context is important, then you're going to go into what is called recurrent neural networks, and if you need to remember what your previous decisions were, then so if memory is important in the process while you're doing this, and then you would go into what is called long-term, short-term models, which is the LSTM class of models. So these are very popular models also. We're not going to have time to go through that in this class, but there are some good articles on these. And I'm going to put a link to one of those so that you can go and look into when and why you would use these other ones. All right. Okay, so let's go back to our notebook and see if that's done. Oh, cool. So the deep network here, so while the neural network took 30 seconds, the deep network took a little longer, which makes sense. It has a whole other layer to go through. And so the lowest is F1 score is 0.96. And even here, the lowest was 0.96. So in general, maybe the performance not very different, right? You got 0.898, 0.99. Yeah, the performance seems to be about the same. It takes a little longer, but over time, as you have more complex problems, it might be more and more worthwhile to build deeper networks. All right, guys. So before we wrap up today, there is one other topic I want to go through, and that is, so far we've just done a train and test split, right? We take our data set, we take this data set, and then we split it into train and test. And then we go ahead and we're saving the test set to be able to evaluate how well our models do. So let's go here and talk a little bit more about that. So suppose we have, we have a data set, and we've saved, right, in our examples, we've been doing 20% most of the time. So we take a random 20% sample, and we save that for testing, right? So we save this for testing. This is a random 20%, and then the remaining random 80% is used for training, right? But what if we were just lucky in the way that we randomly picked these samples, and it always gave us good, it gives us good results, right? But if we had randomly picked another set, it may not have gotten good results. So one way to make sure that our models are actually good is to run a few experiments. So let's say what we've already done is experiment 1, and then what we would want to do is, take a different chunk and use that as the test set. And then maybe take the third chunk and use that as the test set, and then the fourth chunk, and then the fifth chunk, right? So this will make sure, so if we use these as our test sets, so you got experiment 1, 2, experiment 3, 4, and 5. If we were to run 5 experiments, and then with the model we've already built, right? We've already built the model. So we take our model, let's say deep neural network for the digits. We take that model, and then we take our full set X and Y, and we we split it into 5 experiments, and we want to randomly, take 5 experiments means it'll automatically do 20%, right? If we said 4 experiments, it would be 25%, right? So it would break it up into 20%, 20% each, and run this, you run the model on this testing set and this testing set and this testing set, and then give us the performance of each one of those, right? That then would give us more confidence that the model that we've picked, didn't just get lucky with the test set we picked initially. It actually works across, any random test set. So this whole process is called. So this whole process is called cross-validation, because we are cross-validating our model, right? So what we don't want to see is that we have a really high performance for one of these, and or high for some of them and low for some of the others. That means the model works well for these sets, but not so much for these. That means we need to go back and revisit this model, right? So let's go ahead and run that and see how well our model can be cross-validated. All right, so if we go back here, look for some. Let's look for some syntax. So we have sklearn cross. So cross-val score is the function within sklearn that gives us the score that we want for each one of them, and then it's under model selection. And if we go look at the syntax here, we've got model selection cross-val score, and all we need to do is call cross-val score, the name of the model, their model is called Lasso, and then pass in X and not train and test. Remember, we're passing the whole X and Y because it's going to go through different train and test within that. And then the number of experiments, which is also called the number of folds. Okay, so let's bring that into our notebook. We know that it's in model selection. So let's just say we are doing cross-validation, and we have that piece of code. Well, we want to, from sklearn.model selection, import cross-val score, and then cross-val score, but we want to do it with the model deep neural network for digits, X and Y. This is still our X, this is still our Y, but we wanted 5 folds, right? And the number of folds, can be changed. Because we're doing 20%, we could probably just go with 5 and see what happens. All right. And so when this runs, we should be getting, performance values for every fold, right? So going back here, we want to look at what each of these values are and make sure that all of them are high, and it's not just high for some and low for the others, right? So let's go on mute for a couple of seconds here while this one runs. All right, one more thing I'd like to mention, as that's running is what are some of the takeaways from class today, right? We've learned how to take, first of all, take visual data and and be able to take a look at or visualize data that actually has, pixel data. And then we were able to look at, comparing, traditional SVM models with neural network models. And then we improved, and then we tested our model here with some new data. We built a deep network with additional layers to see if it would help. But then when should you, something that you should be careful about is that you will see that in industry, people would go and run neural networks. I mean, if it's faster, why not run it, right? That's what most people do. They'll say, okay, well, I don't want to go and build this model and take 6 minutes, or, bigger models will take much longer. Why wouldn't I just go with neural networks and build one that's much faster and still get the same or better performance? Well, the thing is that, with SVM and with logistic regression, with some of these other models, you can, with SVM, with logistic regression, especially with naive Bayes, you can explain these models very well. So if you are predicting something like, should somebody get a loan or not? Or if you're predicting something like, is this transaction fraud? Then you really want to be able to explain yourself, right? Saying, hey, if you denied my loan application, can you tell me why? It's better be not because of my race or gender or age or something like that. There should be a good reason. Whereas when it comes to neural network models, because these are all weights and biases, it's kind of hard to explain. But there are some best practices. So what we would normally do is, we normally suggest that, whenever you start a model, if it takes a long time, you may consider neural networks. but think about what you want to be in each layer instead of just letting the model pick its own layers. So here you remember we thought about, you know, partial images as the first layer and more complete images as the second layer, and then putting them together as the digits. So we have some reasoning behind the layers. So if you have some reasoning, then you'd be able to say, hey, the reason this was predicted to be a 9 is because it had a circle and a line. And why did it have a circle? It had a circle because it captured all of these. And so even if it misrepresented something, you can go back and say, oh, maybe I need to tweak this weight, or maybe I need to increase the bias or something to be able to properly capture that. Okay. So those are some things that we would want to watch out for. All right, cool. So cross-validation is done. You see that we got 5 values here because we put in 5 folds, and 0.97, pretty much 0.97 across the board. So we are essentially good to go because we have a nice high value for our first fold, another nice value for our second one, third one, fourth one, and fifth one. So all of them are good. If we had seen that one of them was 0.8 or 0.7, something lower than that, we might say, all right, no, we got to go back and retrain our model. Okay. All right, guys. So with that, we'll wrap up for today.